Hello everyone, my name is Mateus and welcome to this talk on commensurating H&N extensions and Bioautomaticity. This talk is going to consist of two parts. In the first part, I would like to introduce bioautomatic groups, tell you a bit more about relationship between bioautomaticity and various notions of non-positive curvature, as well as introduce two results, one of which is based on joint work with Sam Hughes, telling you that we can't, for certain classes of non-positively curved groups, we can't say in general that these groups are bioautomatic. And in the second part of the talk, I would like to tell you a bit more about the proofs, and in particular to say what sort of geometric structures we can put on a given bioautomatic group. So let's start with some motivation for why we should study bioautomaticity. Well, historically, bioautomatic groups arose in an effort to generalize hyperbolic groups. So in hyperbolic groups, we know that geodesics in the Cayley graph satisfy some nice properties, both algorithmic and geometric. And we would like to generalize this for more general classes of paths in Cayley graphs for more general classes of groups. As one of the main consequences of bioautomaticity is their computational properties. So given a bioautomatic group, we already know how to solve the word problem in this group. And in particular, bioautomatic groups are finally presented with at most quadratic Dehn functions. So the solution of the word problem is quite efficient. We also know how to solve the conjugacy problem in any given bioautomatic group. And in this talk, I would like to concentrate more on the geometric properties on bioautomatic groups. In particular, I would like to somehow convince you that many groups which have non-positive curvature in one or another form are actually bioautomatic. On the other hand, many bioautomatic groups that we know come from some geometric context of non-positive curvature. Okay, so having said that, let's define what it means for a group to be bioautomatic. So suppose G is a group generated by a finite subset X. We call this set X an alphabet. We think about it as consisting of some letters. And for simplicity, suppose that X is equal to X inverse and contains the identity. So it's a symmetric generating set containing the identity. And we have a projection from the free monoid to G, or from the free monoid on X to G, which is just the monoid homomorphism given by taking a word with letters in X and multiplying them together to get an element of G. Suppose, in addition to that, we are given a subset L of X star. And in this case, we say that X comma L is a bioautomatic structure for G if the following three conditions hold. The first condition is algorithmic. So it says that L is a regular language, or in other words, it is recognized by something called the finite state automaton. What does it mean? Well, it means there is some finite graph with edges labeled by letters in X, which allows us to sort of read off words in X star. And there are some rules to decide whether these words will be in our subset L or not. So there is some finite graph somehow which allows us to define this language L. Another condition is that given any group element, the number of words now representing that element is obviously we require it to be at least one, but we also want for any group element to be represented by at most finitely many words. And the third condition is more geometric. It says that there exists a constant k such that paths labeled by words in L with endpoints distance at most one away in the K-graph of G. So we have the following situation. We have two paths in the K-graph labeled by words P and Q in L, such that the starting and the ending points of these paths are distant at most one away. These paths satisfy so-called K-fellow traveler property. Which basically means that we pick a non-negative integer t, and we travel along the first path, distance t, and we travel along the second path, distance t. We arrive at these two blue points, and these 2 points, regardless of the choice of t and the choice of our paths, will be distance at most k away from each other in the K-graph. So these are the 3 properties defining a bioautomatic structure, and we say a group G is bioautomatic if it has some bioautomatic structure. Right. So these are the groups that we would like to study, and let's see some examples. Well, as I mentioned before, the first example are negatively curved groups or Warm hyperbolic groups, in which for the language L we take all geodesics, labels of geodesics in a given K-graph. We also know that so-called flat groups or finitely generated virtual abelian groups are also bioautomatic. A slightly more complicated example, again, possessing some sort of non-positive curvature, are cubulated groups. So these are groups acting properly and co-compactly on K0 Q complexes. For those paths, for those Q complexes, we can have a nice collection of paths which allow us to define some regular language in the K-graph of a cubulated group, satisfying the axioms of bioautomaticity. We may also generalize hyperbolic and cubulated group example to so-called Helly groups. So these are groups which have been introduced recently in geometric group theory, and they are acting geometrically on some class of graphs called Helly graphs. Some particular Helly groups include hyperbolic groups, cubulated groups, small cancellation groups, and various other non-positive curved classes. A very recent result says that Coxeter groups are all bioautomatic as well. So in here, we know that Coxeter groups have some cubulation, but they are not co-compactly cubulated. So in general, if we're given a Coxeter group, it will act on some cube complex, but not co-compactly. But nevertheless, we can pick some language over a Coxeter group to show that these groups are bioautomatic as well. There are some nice closure properties that we would expect. So direct products, free products, or graph products of bioautomatic groups are bioautomatic. Groups hyperbolic relative to bioautomatic groups are bioautomatic as well. So all these nice combination properties. And what we would like to have as well is that finite index subgroups of bioautomatic groups are bioautomatic. Although I should mention that bioautomaticity is not known to pass to finite index overgroups. So it is not known if there exists a virtually bioautomatic group that is not bioautomatic. Okay, but anyway, this gives us some nice classes of groups which satisfy some sort of non-positive curvature, and we can show that these are bioautomatic. Now, what are some obstructions for bioautomaticity? So what can prevent a group from being bioautomatic? The first obstruction has been mentioned already. So it is that bioautomatic groups are finally presented and have at most quadratic Dehn function. So groups like out of n, which have a superquadratic then function are not bioautomatic, or groups like Reith products, G, Reith H, where H is an infinite group, they are not finally presented, so again, they're not bioautomatic. And another abstraction comes from looking at cyclic subgroups of bioautomatic groups. So it is known that in any bioautomatic group, cyclic subgroups are undistorted or quasi-isometrically embedded, which means that there are no infinite order elements in a bioautomatic group acting on the Cayley graph in some weird way. So for that, that allows us to exclude some groups from even being subgroups of bioautomatic groups. So in particular, Bamstock-Solta group, BSPQ, is not a subgroup of bioautomatic group unless P is equal to Q in absolute value. And we know that if we have a finitely generated virtually nilpotent group that is not virtually abelian, that again cannot be a subgroup of a bioautomatic group. But these restrictions do not always apply. So in particular, we have some specific classes of groups for which these restrictions cannot be applied to rule out bioautomaticity. One such class is so-called semi-hyperbolic groups. So semi-hyperbolicity is defined in a very similar way to bioautomaticity. The difference is that we replace the requirement for this language L to be a regular language by some weaker condition. So this gives a larger class of groups, and it is known that there are semi-hyperbolic groups which are not bioautomatic, but we may ask about some nice subclasses which satisfy nice geometric properties. One of these subclasses is cat-zero groups, so groups acting geometrically on cat-zero spaces. We may ask, well, are all cat-zero groups bioautomatic? And another such subclass is so-called hierarchically hyperbolic groups, or HHGs. So this is slightly more complicated to define, but just as some examples, hierarchically hyperbolic groups include hyperbolic mapping class groups, most, conjecturally even all, co-compactly cubulated groups, groups acting nicely on Provisov cat-1 spaces, and so on. And they again satisfy nice closure properties. So this is a big, nice class of groups, which again satisfies some strong geometric properties. Okay, so here are some answers to these questions. And the answer is that it turns out that in general, we can't say anything about all cat-zero groups or all hierarchically hyperbolic groups. The first result in this direction is due to Ian Lear and Nashon Minassian, who showed a couple of years ago that certain nice, not too complicated cat-zero groups actually cannot be bioautomatic. And this can be strengthened to say that the same cat-zero groups, when they are not bioautomatic, they also cannot be subgroups of bioautomatic groups. So this is the first result that I would like to present, that the same groups introduced by Ian Lear and Nashon Minassian also cannot be even subgroups of bioautomatic groups. And the second result I wanted to present to you concerns HHGs. So in a joint work with Sam Hughes, we showed that there also exist HHGs which are not bioautomatic. And here I would like to take the chance to advertise Sam's talk, which is given in a session on Dirac-Miller spaces and geodesic currents, where Sam will tell you a bit about this scary looking thing of geodesic currents. So this is a concept coming from low-dimensional topology, which allows us to study bioautomaticity. So there's a nice connection between these spaces and the groups that we study, the hierarchical hyperbolic groups that we study. Okay, so yeah, please check Sam's talk as well if you are interested. Now, for our groups, what they are, how can we define them? They are quite nice, and we construct them as groups acting geometrically by isometries on T cross V, where T is some locally finite tree, and V is either the Euclidean space, R to the n, so I will call this the Euclidean case, or the hyperbolic plane. So I will call this the hyperbolic case. And such a nice action is already enough to say that our group gamma is ket 0 in the Euclidean case or an HHE in the hyperbolic case. So we only need to rule out bioautomaticity at this point. And to do that, we look at the action of gamma on T. So in our groups, this action is quite nice. And in particular, it has one orbit of vertices, has no edge inversion, and the vertex stabilizers under this action are either Z to the M in the Euclidean case or a surface group in the hyperbolic case. And another property that we may use is that since our group T, our tree T is locally finite, G is commensurated in gamma, which means that given any conjugate of G, we may intersect it with G and look at the index of what we get in the whole vertex stabilizer G. This index turns out to be finite regardless of which conjugate we take. So these two properties, the properties of the action on T and the fact that G is commensurated, allow us to give an algebraic description of the group gamma. So algebraically, it is a commensurating H&N extension, G star phi, where phi is just an isomorphism between two finite index subgroups of G. And the last property that will be important for us in our proofs is that if we look at the projection of P, the projection P of gamma to the isometry group of V, given by just looking at the action of gamma on V, we can give topology to the isometry group of V. So in the Euclidean case, this will be R to the M, G to GLM R. In the hyperbolic case, this will be PSL to R. So in both of these cases, we know that this projection will have a non-discrete image. Okay, so these are the groups that we want to study. And I would like to introduce one of the main ideas that we use in our proofs, which is L quasi-convex subgroups. So in here, let's suppose that we are given a bioautomatic structure for gamma. Let's call it X comma L. And we say that a subset S of gamma is L quasi-convex if the following happens in the Cayley graph of gamma. So we look at the Cayley graph of gamma, we look at subset S as a subset, and we look at paths with endpoints in our subset S labeled by words in the language L. So we say S is L quasi-convex if there exists some universal constant K such that all such paths will be in the K neighborhood of S, meaning that if we are given a point in one of those paths, this will be distance at most K to S. And this is particularly useful when S is a subgroup. And in particular, we can, in that case, we can find actually some quasi-convex subgroups algebraically, as well as say something, some properties of these quasi-convex subgroups. So this is a theorem of Gersten and Short, which says that if we are given a bioautomatic structure X comma L on gamma, then the centralized of any finite subset of gamma will be L quasi-convex, regardless of which X and which L we take. So this allows us to find L quasi-convex subgroups. And we can also say something about these subgroups. In particular, these subgroups will be biotomatic. And a further property that we will use is that there will be a biotomatic structure for an L quasi-convex subgroup G that's called Y, M. And this is biotomatic structure is such that any element of G is represented by two words of the same length, one of which is in L and the other of which is in M. So basically, this allows us to study some functions defined as word lengths in biotomatic structures representing certain elements. And for our group gamma, which is the H&N extension of the group G, it turns out that this group G is actually L quasi-convex. So in the Euclidean case, it will be self-centralizing. In the hyperbolic case, it will be up to passing to finite index subgroups and overgroups. It will be a decentralizer of a pair of elements. So this will be a very important fact for us, that this group G will be L quasi-convex with respect to any biotomatic structure on gamma. Okay, so let's look at some ideas for the proofs. So suppose X, L is a biotomatic structure for a group gamma, and the main tool that we will use in our proofs is so-called L translation length. So given element of the group gamma, we look at the length of the shortest word in L representing that element, and we look at a stabilized version, which we call, in this case, the L translation length of gamma. This is the limit ascent tends to infinity of the length of the shortest word in L representing gamma to the n divided by n. So this function defined like that is positively homogeneous. This follows straight from the definition. And I mean by that the L translation length of gamma to the n is the same as n times the L translation length of gamma for any n at least one. And now we use the fact that our subgroup G is L quasi-convex. This allows us to find a biotomatic structure for our subgroup, which have the same translation lengths as we had originally. And we use the fact that our subgroup G is also commensurated. Saying that it's commensurated allows us to say that given any element small g in our subgroup G, and any element small gamma in our group gamma, there will be some positive n such that gamma G to the n gamma inverse will be an element of the group G. And that allows us to define a gamma action on the set of all positively homogeneous functions f from G to, let's say, 0 infinity. And the important thing here is that the L translation length is invariant on the gamma conjugacy, which is easy to check from the definitions, which means that this action that we just defined fixes the M translation length associated to the biotomatic structure on our group G. And the last step, which I will talk a bit more about in the second part of the talk, and Sam is going to tell you more about this as well in the hyperbolic case in his talk, is that we may define some boundary of our vertex stabilizer G, of our base subgroup G of the H&N extension. And this function will satisfy some nice properties which we can use to obtain a contradiction. Okay, so that's it for now, and I hope to see you in the next part of the talk.